Hello and welcome to this presentation, where I will be discussing our study, Casual Users and Rational Choices within Differential Privacy. My name is Narges Ashena and I'm a PhD candidate at the University of Zurich. This is a joint work of my colleagues Oana Inel and Badri Persaud and my supervisor Ibrahim Bernstein. Let's begin with a brief reminder about differential privacy. Differential privacy, abbreviated as DP, is a privacy framework that ensures the results of a query on a dataset remain approximately the same whether or not any individual's data is included or excluded from the dataset. This way, it allows us to gain approximate insights from the data while protecting privacy at the individual level. DP's privacy protection is quantifiable, and it is achieved at the expense of losing some degree of accuracy by adding carefully calibrated noise to the query result. The parameter epsilon in the DP framework acts as a knob to calibrate the noise, therefore controlling the level of privacy protection and the corresponding loss of accuracy. Epsilon takes positive real values. A bigger epsilon results in adding a smaller noise, therefore providing less privacy protection and a more accurate result. Conversely, a smaller epsilon increases the level of added noise, providing higher privacy protection and losing more accuracy. Setting epsilon is hard, and it remains one of the challenges in employing DP in real-world setups. The DP experts recommend keeping epsilon smaller than 1, ideally at the level of 0.1 or 0.01, depending on the sensitivity of the data. According to a blog post, in real-world applications of DP, a wide range of epsilon values can be seen, from 0.1 to nearly 50. But what about day-to-day users, real data owners' opinion and preferences about DP and epsilon, as they are the immediate targets of privacy risks and threats? In this study, we aim to explore effective ways of communicating DP and epsilon to casual users and to investigate their perceptions and preferences regarding differential privacy and the epsilon setting by exposing them to an explicit and realistic view of epsilon on a continuous scale. We developed multiple interactive visualizations that allow our participants to adjust epsilon values and directly observe the impact of DP noise on privacy loss, accuracy loss, or a full trade-off. We tailored these visualizations to a well-recognized practice of reporting COVID-19 positive cases in the famous city of New York. To visualize privacy loss, we used a pie plot highlighting the probability of inferring an individual's COVID test result correctly from the published counts. For instance, for epsilon equal to 0.25, this probability is around 12%, as shown by the picture. For epsilon equal to 2.5, this probability is about 71%, and for a very high epsilon of 4.5, it reaches almost to 90%. For accuracy visualization, we used a simple line plot as shown in this slide, with the solid line showing the original counts and the dotted lines showing the noisy counts. The shaded area highlights the error bound of DP for the selected epsilon. Here we also have a snapshot of this visualization for two more epsilon values. Please note that although the noise bound remains constant for each epsilon value, the error bound can look very different relative to the magnitude of the original counts. For example, for the same epsilon values, there is barely anything visible when the counts are scaled up 50 times. Illustrations of accuracy loss can be more contextual, like this heat map of New York City showing how DP changes the COVID counts as we navigate through different values of epsilon. This is an example of how our interactive visualizations work in action. In this particular example, the map on the left is static as a reference for comparing actual and noisy values. Considering the privacy accuracy trade-off, each side separately and or together, and two levels for relative accuracy loss, and three plot types that I showed you, pie plot, line plot, and map plot, we ended up with 9 different visualizations to possibly communicate dp and epsilon to the users. We added one extra condition, only with the slider and no visual aid as a baseline. Ideally, people's selection should be based on their privacy preferences and be smaller than one following the expert's recommendation, and not dependent on these varying conditions. We conducted a between subject study involving 426 participants. We provided them with a brief introduction to DP with a short video and a text, and then we presented participants with the New York data sharing scenario and randomly paired each participant with one of the 9 visualizations or no visualization as a baseline. We asked them to interact with the assigned visualization and select an appropriate value for epsilon for the given data sharing scenario. We also collected additional information such as participants' privacy preference scores and their comfort level with different entities deploying DP. For more details, please read our paper. All right, here you see the distribution of selected epsilon for each condition ordered by the group's median. First, we see that about 75% of the participants selected epsilon in the lower half of the slider. This is a good sign because it shows that participants, although given more options, opted for smaller values for epsilon. However, these choices were generally above the recommended values by DP experts. Here, the line is at 0.25. If you recall from the earlier slides, 0.25 is one of the recommended values by Harvard's differentially private data sharing interface called PSI. We also see that 8 out of 9 visualizations demonstrated improvement over the baseline in leading people to select smaller values for epsilon or closer values to the expert's recommendations. And 4 of these conditions show a statistically significant impact compared to the baseline. To see if changing the accuracy loss level had any effect on participant choices, we first grouped conditions with the same accuracy level together. We realized that when people encountered low accuracy in the published data, they opted for bigger epsilons, and this effect was statistically significant. Running a similar analysis on the plot type did not show any impact on selected epsilons by participants. All right, here are our takeaways. First, privacy-focused visualizations seem to be effective in leading users towards choosing smaller epsilons and epsilons closer to the values recommended by DP experts. Second, we find that participants are sensitive to the level of accuracy loss presented to them, and they might feel the need to give up their privacy for more accurate and useful results. Third, exploring additional data sharing scenarios could provide more insights into users' choices and perceptions. Finally, we need to come up with effective ways to visualize DP and epsilon for more advanced concepts and mechanisms in differential privacy framework. You can use this QR code to access the full paper on IEEE library. Thank you for your attention.